Hi, I'm Adrienne Marshall. I am an assistant professor at the Colorado School of Mines. I am faculty in the Hydrologic Sciences and Engineering program here, and I have a departmental home in geology and geological engineering. My research areas are snow hydrology. I do some work on ecohydrology and boreal forests. I do some hydrologic modeling. And I also work on water in the energy system. The big thing that unites all these topics is understanding how climate change is impacting our water resources. I got my PhD at the University of Idaho with your instructor for this class, Megan. Before that, I did a master's in energy and resources at Berkeley and an undergraduate degree in biology at Scripps College. So if you ever want a role model for getting degrees in different areas and having your career kind of wander, that is definitely what I've done. And I have felt like that kind of enriched where I ended up now. Megan asked me to say a little bit about how I got into this field too. I will say the background for me came from a real love for the mountains and being in the mountains. So after I finished my undergrad degree, I really didn't know what I wanted to do career-wise. I started working in environmental education in California, so partially in Yosemite, and a lot of that was working with K through 12 students, taking them into Yosemite, showing them around, doing some science, but really a lot of like hiking and personal growth for them. And I was also at the same time doing like big long distance hikes when I got a chance to take some time off work. And that's what I was really passionate about. And when I started feeling like I wanted a career with a little more stability and room for growth is when I went to grad school. And I had this love for the mountains and this feeling that climate change was a really scary problem when I thought about the mountains and how they connected to people. So, especially like via water that falls as snow in the mountains and is this super necessary resource for cities downstream. And it felt like this sort of terrifying and overwhelming problem. And so that's kind of how I got interested in and excited about studying climate change and trying to understand it a little better to make it a little less overwhelming, if still serious. That's how I got here. A lot of the importance of snowpack in the Pacific Northwest is comparable to how we think about snowpack in lots of mountainous regions. The biggest way I think about it is that it acts as a natural reservoir for water. You probably know that in a lot of the US, dams and reservoirs have historically been really contentious. Like there's been lots of environmental litigation over whether we should have dams and how we should operate them. And snow is kind of this like natural reservoir that's politically not problematic, and it holds our water until runoff can happen later in the year. So that means a couple things. It holds soil moisture longer for plants. So when we start worrying about losing snowpack, we're worried about a longer summer dry period. It insulates soils in the winter. So snow is a great insulator. So it has an impact on like what's the temperature dynamic for the soil under it. Another important thing snow does is that it reflects a lot of light back into the atmosphere. So you might hear the term snow albedo feedback. Essentially, since it's brighter than the surrounding surface, it has an impact on our climate by reflecting lots of that energy back out. And then really to focus in a little bit more on that factor where it creates later runoff. A couple things I think about are that our water resources infrastructure is really built for a world where we have snow that holds water in the mountains and has that runoff happening later in the year. So when we think about like how big are the dams we have, how are our water resources allocated, they're kind of built assuming that that snowpack is there. SWE stands for snow water equivalent. So if you were to go out into the mountains and look at snow that's on the ground, it might be this deep, but if you melt it down, you might get this much water out of it because the snow is comprised of water and air. So the snow water equivalent is the depth of snow that is present in snowpack on the ground. One thing about snow water equivalent is you can measure it at any time that there's snow out there. So when we think about it over the course of a snow season, we see it varying over time. SWE max, or peak snow water equivalent or maximum snow water equivalent, those are all equivalent. That would be if you looked at one point on the ground, what's the maximum value of that snow water equivalent that you get throughout the year. So it's kind of one summary statistic per year. It used to be that April 1 snow water equivalent was treated as sort of a proxy for the date of peak snow or SWE max. That's sort of increasingly thought to be not the case as we're seeing our timing of SWE max advancing earlier in the year. One reason we had that date proxy is really sort of technological. So back in the olden days, the way we got snow water equivalent was people would go skiing out in the mountains and do snow surveys at a bunch of different locations and see how deep the snow was and what the water equivalent was. You can't practically do that every day. So typically they would do it like maybe once a month in maybe like March 1st and April 1st is pretty typical, sometimes with the February or May added on. But we didn't have a continuous time series of how much snow was out there. In the past 80 years or so, we've gradually accumulated more SNOTEL stations, which SNOTEL is short for snow telemetry. So those sites give us a continuous time series of snow water equivalent at individual points in the mountains. So we no longer have to rely on April 1 snow water equivalent. We can look at our peak snow water equivalent, and we can also look at when that peak occurs. Snowfall equivalent is this SFE SPE. We usually don't have to say it out loud. So that's the liquid snowfall equivalent, like water that falls out of the sky. So sometimes we'll see like a SFE to P to precip ratio. And then we're looking at like of all the precip that fell, how much of it fell as snow. If you think about SFE, so snowfall equivalent coming out of the sky, and then snow water equivalent on the ground, the difference between those is really how much melted, depending on when you're thinking about. So that's why we differentiate those terms. For one thing, they tell you different things over different time scales. So that peak SWE that we looked at is like a summary statistic describing SWE. And then snowfall equivalent versus snow water equivalent. Snowfall equivalent tells you about the amount of water or snow water coming into the system. Snow water equivalent tells you about the amount of snow water that remains in the system. It used to be that the sort of mental model was that over the course of the winter, all the snowfall equivalent that fell was essentially present at the date of peak snow water equivalent, like that really over the winter snow only accumulates. But especially with climate change, we have some pretty good evidence now that winter melt has increased. So you might have snowfall equivalent that then melts and makes it such that like your peak snow water equivalent is not the same as the sum of your snowfall equivalent up to that point.